It's great to be speaking on the same day as two of my collaborators in a rival workshop. Friendly rivalry, of course. The motivation is that in a theory of quantum gravity in more than 3 dimensions, and dimensions as well, there's going to be more than just Einstein gravity, possible superpartners, and possible spin 1 gauge fields. There's going to be an infinite power of higher dimension operators in the effective action, which become more and more important as you go to high energies. So I'll write a few here. And the conventional wisdom is that we'll be able to learn a lot about quantum gravity. We can figure out the Wilson coefficients with which these appear. Now, a possible way to attack this problem is to go to ADS, because that gives you access to non-perturbative methods that apply to conformal field theories, in particular the conformal bootstrap, supersymmetric localization. And within the last 5 years, there's been some progress towards this goal in a variety of cases. These include the maximally supersymmetric theories in 3 and 4 dimensions, of course. But also, more recently, some 3 and 4D theories with 8 supercharges instead of 15. The papers for these might be too numerous to list, but 4D n equals 2 is done in my work with Shai and Pietro. And for 3D n equals 4, there's a recent paper by Sylvia Shi and 2 of their respective former students. And I will probably show some inevitable bias towards this case, but at the beginning, has to be right. So let's start with 4D n equals 4. So a basic observable in ADS 5 plus S5. And just to be a little about what this is in the CFT, the graviton is dual to the stress tensor multiplet, which is a Lorentz scalar of dimension 2. And with respect to SO6 symmetry, is a 2-index traceless symmetric tensor. So what you can do is saturate the R symmetry indices with null polarization and get this object which handles the entire R symmetry multiplet at once. And the non-trivial part of the 4-point function will have 2 cross ratios with respect to the x's and 2 cross ratios with respect to the t. And they'll have some protected piece, which I'm not going to write, which can be computed with the SCFT chiral algebra correspondence. It doesn't depend on the marginal couplings at all. And then it's going to have this piece on which I'm going to focus. And the reason this decomposition exists is because the stress tensor multiplet is half BPS. So this is going to obey a superconformal word identity, which has this form. And this is a formal suit. So we're used to thinking of this correlator in a double expansion for large n and large lambda. N takes care of n is related to the genus of the world sheet, and lambda is related to the powers of alpha prime or the string length through a relation like this. The first term is Einstein gravity. Yeah, cross ratios. Yeah, okay, maybe I'll write that. And this is a shifted version of the 1 over STU amplitude, which holds in flat space. And then you have the first stringy correction at order 1/n². The amplitude for a contact interaction, which means a polynomial Mendelssohn variables. Next, you can write a subleading r⁴ correction, not 1/n⁴ and a different power of the tough coupling. Then what you have is loop level supergravity. And I'm going to write it in this way to emphasize that it can be computed by unitarity cut, which builds one loop correlator out of two tree level correlators. And unitarity cuts have ambiguities at low spin, so that means we should also add something like this. Where this is again a contact interaction, it's again a polynomial, as it better be if it's going to have finite supported spin. And maybe one thing to emphasize is that this term is not just an artifact of how much we like unitarity cuts. If we were to do a more old school calculation using explicit Witten diagrams for all the clues of prime modes, we would again have a low spin ambiguity simply because the gravity is not finite. So this is the expression that gets written most often. It's called the strong coupling expansion. But what we can also do is go to a limit where the Yang-Mills coupling or the string coupling is fixed to a finite value, leading to something called the very strong coupling expansion. And in this case, first term of the amplitude is the same. But then if you set the tough coupling equal to g²n, you get 1/n⁷ times some power of g. If you plug it in here, you also get 1/n⁷, but times a different power of g. So the stringy correction will be 1/n⁷ times some function of G Yang-Mills. But instead of a function of G Yang-Mills, it's you might as well also include instanton effects and write this as a function of the complexified Beach coupling tau. So this will be did I get that right? And then you can consider loops and so on. So these Wilson coefficients, the B's, either in this formulation or this one, will be the ones that I'm interested in fixing using the bootstrap and localization. Absolutely. Yes. Yeah, so this one's a constant. This one has a linear term, which can be mapped to flat space, but also a constant term, which is changing ABS. Kind of like how these have the leading power and the lower power. I don't think so. It's, oh, okay, yeah, that's true. So because the degree is low, it's coincidentally the case that they're both. Yeah. So you mean which fractional powers can we predict ahead of time? You probably can, but I don't know the answer. Um, but yeah, there's a non-trivial reorganization of the terms. 1/n is the only. Yes. Yeah. There will be at least all even powers. Well, um, if we believe that we have a UV complete theory, we just don't need alpha prime to be small. We don't need to expand. Yes. Um, well, I don't know what diagrams do, but beyond just the diagrams, non-prescriptive effects will also be important. Yes. Yeah, that's why I'm with how the well the only way I know to derive it is the technique I'm going to talk about. Yeah. Yeah, sorry, I don't know what else to say other than finite and finite gauge coupling makes sense in a gauge theory. So when you have something, if you had some expansion that is way too hard for us to figure out, amplitude, then after the fact you could expand it 1/n if you wanted to. And yeah, maybe one. Okay. Yeah, thank you, Eric, for answering or partially answering her. But yeah, you won't get n to the 1/4 for sure, but you will get powers into n. That's true. Yeah, yeah, you can think of the Planck length as you think. Yeah. So I sort of made it sound like you can have 1/n⁷ times an infinite series in GM knows, we sum that into a function here. But in all of the cases where we can actually fix this function, it'll turn out that this is protected vertex. We'll label it vertex again. This is a vertex, which means it's a finite series in GM knows until into the infinite series of infinite contracts. Are unprotected vertices as well, where the perturbative and non-perturbative terms are both infinite in number, but those seem to be beyond the reach of localization so far. Now, going through this procedure has been given a name, which some people like and some people don't. And that name is bootstrapping string theory. And you could say this name is applicable whenever you're dealing with a theory that has a marginal coupling that can be put to 0. If you look at these 3D holographic theories, though, they don't have a gauge coupling. They have a Chern-Simons level, which is an integer. And if you're not taking the asymptotically large, then you're looking at fixed, isolated superconformal field theories, which only admit this type of an expansion. And therefore, you should call this bootstrapping M theory. And for the case of 4D(n=2), you again have a. So one of the theories I'm going to talk about has a gauge coupling, which can be taken to 0, giving you an example of bootstrapping string theory. But the n=2 landscape also includes isolated superconformal field theories, which can be reached gauge theory by an RG flow, and the gauge coupling has to be at some fixed point value. And this is exactly what happens in F theory. We have these various cases. Now, for the M and F theory cases, I don't know any right now that can compete with the bootstrap plus localization one. But for the case of string theory, I have to mention the work of Alday and Henson. We showed that the tree level part of this expansion, namely the Virasoro amplitude, a compelling conjecture where it can be written down by using the constraints of dispersive sum rules at high energy and single valuedness. And that gives something that's a bit complementary. So instead of here, where we work exactly within ADS, but we only fix a finite number of Wilson coefficients, they are able to fix infinitely many powers of the tough coupling, but they approximate ADS by expanding around flat space, which is arguably closer to the original motivation method. So this is a very promising alternative method. In order to compute Wilson coefficients that cannot be done in this way or this way, what you would have to do, I think, is string theory in ADS, and this faces the famous problem that the RNS formalism cannot handle the Mondrian flux, so you'll need something else like the pure Spooner formalism, which is still being developed. But if you say, I don't care about ADS, can't we just get these Wilson coefficients in flat space by doing ordinary string theory? Of course you can. But because of the loops involved, the calculations will be very hard, so they haven't all been done. But if you look at the calculations that have been done and compare their Wilson coefficients to the I'm going to show you, they agree, and this is a check of ADS. So what I do now is modify this construction a little bit. So I've always thought it's a bit semantic whether you say that using localization, because in 4 dimensions, there's like there are 2 homological constructions. There's the chiral algebra where the operators in the cohomology, and then there's localization where the operators in the cohomology are Coulomb variant. But in 3D n equals 4, there's mirror symmetry between the Higgs and Coulomb variants. So yeah, you can sort of doing things one way, like using the chiral algebra, it sort of looks like you're doing localization. Using localization, it looks like you're doing the chiral algebra. Okay. Indeed, I don't know localization. I don't know any localization approach because it's a non-Lagrangian theory. But there is indeed a protected chiral algebra. And I remember you had a paper with Chai finding all order predictions from the structures of chiral algebra for Deepon coupling. Yeah. Yeah, so maybe I should have mentioned that as well. Yeah, so there's the technique I'm talking about, there's Alday and Henson, and then also some W output technology. So that's what I wanted to say about n equals 4 super nose. We can of course come back to it later. But the brain setup for n equals 4 super nose is a stack of many D3 brains. And roughly speaking, these give you n equals 4 because a string that ends on one of these brains has to end on another one. And the representations given by these two endpoints lead to adjoint matter. And n equals 4 super Young-Mills is a special case of n equals 2 super QCD with adjoint hypermultiplet. And it is at low energy supergravity on ADS5 cross S5. But now is have these D3 branes probe a small number of 7 branes, where now you can have fundamental matter as well, because this thing can go from here to there. And because you have a small number of 7, the near horizon limit is also going to include space filling branes. They fill all of ADS and wrap in S3. And the world volume theory here will not be supergravity, it'll be something with spin 1. So super Yang-Mills on ADS3 cross S3, the space spanned by these branes. And there are various types of here. But one example that's especially nice will consist of 4 binary D7 and 1 oriented. And these 7 branes will take the SO6 arc symmetry for S5 and break it to this piece, which looks like the R symmetry of an n equals 2 theory, and also another SU2 factor, which looks like a flavor symmetry. But also, these spin 1 Kaluza-Klein modes will have a gauge group associated with them. So there will be another flavor symmetry, which is a gauge group of the flavor symmetry with respect to CFT. So maybe GF super Yang-Mills. And this might look like a strange thing to do, but there's a lot of evidence by now that it really is the next simplest thing you can do from a bootstrap point of view. So yeah, one of the reasons for that is that just as in the supergravity case where the Kaluza-Klein modes have spin 2, which is just barely big enough. Yeah, it is just barely big enough that you can fit it all within a short multiplet in formal algebra. Just barely small enough. Here, super Yang-Mills Kaluza-Klein modes have spin 1, and that's barely enough to fit in a short multiplet of the any formal algebra. So you have a closed subsector at tree level where everything is half-peak tests. You can use Ward identities and get a lot of mileage out of them. And we exploited this in the paper a few years ago to find the tree level 4-point functions. So these things where instead of R you have F squared, but you can find them for arbitrarily high weights. And they can be organized in sort of a trendy way called hidden conformal symmetry. So if you just solve for the leading Kaluza-Klein mode, you can promote the distances to 8-dimensional distances in accordance with this, and in the extra coordinates collect powers and thereby generate all the higher Kaluza-Klein modes. And then that's the story at tree level. And then at loop level, there are also big simplifications you can see if you neglect gravity. For this, I want to highlight the work of Huang, Wang, Yuan, and Zhu. But in this talk, we're not interested in neglecting gravity. We want to do something complete. And something surprising there is that you also see Pearson, which I hope to get to. Yeah. Yeah, so you can indeed you can compute that with or without Thomas. So this symmetry principle was established by explicit calculation. Yes. So here I'm going to be talking about the analog of for graviton amplitude, which will be the for gluon amplitude. This will be essentially the same thing. A half S dimension 2 scalar, which has the R symmetry dependence saturated with commuting SU2 spinors. But there's also a joint index with respect to this gauge group, the bulb. And these being SU2 spinors, they'll lead to a single cross ratio for R symmetry instead of two. So the solution to the supercontrol word identity is going to look the same, except you'll cross out these two and work with the Mellon transform. So now I can write the strong coupling expansion of for gluon amplitude. So it's going to have 1 over n. So the 1 over the flavor central charge instead of the step central charge. Like this. And then the first thingy correction is going to be f to the 4, as you would get from something like a Born-Infeld action. Times this, which is simply constant. And then something interesting here is that you have gravity now. So you have m of r, but it's subleading. It comes in at the same order as, tree level gravity comes in at the same order as loop level Yang-Mills. And in the M theory case that these people looked at, it's even more strange in a sense. It's gravity comes in at the same order as two loop Yang-Mills. Here it's 1. And this amplitude has not been computed yet. It's a little bit strange. So it's tree level supergravity, but the gluons live in 8 dimensions in the 7 brane, where gravity can extend into all 10. So this kind of a Feynman diagram is not so trivial even in flat space. It's not just a delta function of momenta. There's an integration over the transverse momenta that you have to do here. So it starts to not only come in at the same order as loop level Yang-Mills, but it starts to look a bit like the loop amplitude as well. And then here is loop level Yang-Mills. Here is the ambiguity associated with one loop. And then there's something a little bit new, which is that if you go to large Mandelstam variables, i.e. the flat space limit, this loop amplitude doesn't diverge like a power law anymore. It diverges logarithmically, or diverges as s times log f. And this is the divergence that has to be regulated by string theory. So what you need to have is some Wilson coefficient times the log of the tough coupling over n squared with just the right coefficient so that this can combine with log s and give you really log of alpha prime times n. And one way to see that you're not going to get this in the n equals 4 case until 2 loops is that by crossing symmetry, this log lambda needs to appear with something linear and crossing symmetric in the Mandelstam variables. And as Eric pointed out, s plus u plus u in the flat space limit is equal to 0. So really, it's the flavor indices which make crossing symmetry more involved. Like these are the reasons why you're able to have this to the new phenomenon in n equals 2 compared to n equals 4. And I guess one other thing to note is that when you set lambda w proportional to n, then this contact term becomes indistinguishable from this contact term. in the reorganization of the very strong Pelton expansion. And the only reason the one loop amplitude becomes distinguishable from them at all is that this is analytic and Mendelssohn variables, whereas this is absolutely, yes, I should have mentioned this before. So only certain types of seven branes that you can add to the setup are stable, and only certain types lead to a constant axial dilaton background with the requirement to have a conformal field theory. So there's often a basis F theory people talk about for seven branes called B and C, where you label them by their electromagnetic charges. So A is 1, 0, B is 1, -1, and C is 1, 1. And to get a conformal field theory, only seven flavor groups you can get, 7 combinations of branes of each one of these 3 different flavor groups. So I'll write these out. So A0 means no flavor symmetry. A1 and A2, B4, B6, B7, B8. And the associated branes are these ones, where you add a single A each time here. Then here, you have 2 branes added, and then 1 again. This will A to the 4 BC. So A to the 4th, that's the 4D7 branes, and then BC is an O7 plane. Now A to the 5th, BC squared, A to the 6th, BC squared, A to the 7th, BC squared. And if you've read about the classification of any of the 2 theories, then you might guess that these are Argyres-Douglas theories, and these are Mean-Pan-Nemachansky theories. And this B4 case will actually be a superconformal field theory with the Lagrangian again. And maybe one other thing is the allowed value of the gauge coupling or the axial dilaton. So it alternates between I over 3 and I, where here tau can have any value because it's gauge theory, and then it's fixed again. So you can say this is string theory and the other ones are genuine F theory. And yeah, one other thing to help make sense of the literature. So these are the only 7 cases, this exceptional series of gauge groups and flavor groups to get a CFP. But if you don't care about getting a CFP, you don't need the axial dilaton profile to be constant, then there are arrangements of 7 branes that are valid in F theory and lead to an SUN gauge group in the world volume for arbitrary n. And this AN series, this way to get an AN gauge group from 7 branes, does not small n with these ones. So these are exceptional ways of getting no flavor symmetry or SU2 or SU3. So some people distinguish between this AN series and this AN series with 3 entries and the AN series with infinitely many, and referring to an AN configuration versus an HN configuration. And people call these H0, H1, and H2. And now maybe I should say, yeah, and I should also specify what this is. it turns out to be n equals 2 super Yang nose with a USP2N gauge group and 4 fundamental hypermultiplets associated with the D7s and 1 antisymmetric hypermultiplet associated with the O7. And in the formula for the one loop beta function, you can check that this hypermultiplet content makes it 0, which it better be for a CFT. And so this is a certain type of superconformal QCD. Now, it's not what most people think of when they hear superconformal QCD. That's a different hypermultiplet set, which makes it function 0. It would be an SUN gauge group with 2n hypermultiplet, 2n fundamental hypermultiplet, which coincides with this only at the lowest rank K, because USB2 is SU2. And then in that case, the antisymmetric hyper goes away. So this superconformal QCD, which has a different large n limit because the number of flavors and colors grows with n. This is something that some people in this room are trying to study using non-critical string theory. But here, this is vanilla critical string theory. And it has an SO8 flavor symmetry because the fundamental representation of USB2N is pseudo-real. So you can split these 4 fundamental hypers into 8 half hypermultiplets. And that manifests an SO8 symmetry. And that SO8, the adjoint of that SO8 will be what enters here. Okay, so seems like we're roughly halfway through. Yeah, maybe so. So this is the half supersymmetric, the half maximal supersymmetry case in 4 dimensions. I should probably say a little bit about maximal symmetry in 3 dimensions. So this case here, it's kind of similar. Instead of a D3, D7 system in type 2B, you have a D2, D6 system in type 2A, D2 branes localized inside D6. And in the M theory description, this is an orbifold background. So you have some near horizon limit, which is ADS4 plus S7 mod ZK. But unlike the ZK that shows up in ABJM theory, this ZK for n equals 4 has a fixed point. So it acts on, if you parameterize S7 with 4 complex coordinates having this constraint, it acts on them with phases on just the first 2. Whereas in ABJM theory, you would get the same phase for all of them. So this orbifold action has a fixed point found by setting just Z1 and Z2 equal to 0. And then these other coordinates with the constraint would give you more dimensions would add 3 dimensions to the ADS4 locus. And you would get gluons living in a 7-dimensional solution. Yeah, so was there more I wanted to say about the M theory case? Yeah, and one other point is, related to Julia's question. There, the possible groups you have is now 70 gluons when you're bootstrapping M theory. The possible gauge groups are not restricted so much. So here K can be arbitrary, and this is what's called an AK or AK minus 1 orbifold singularity, and it allows it to be SUK. And all of the ADE groups are possible for arbitrarily high rank. So that's different here, different from this one, where the rank can only go up to 8. So I think now I should talk about how the actual calculation of the Wilson coefficients will go. That requires some discussion of localization. So to use localization, you should start with some Lagrangian theory and consider a manifold that preserves nilpotent supercharge and also makes the partition function finite. And then the partition function in this theory has the schematic form, where now you can deform it with some Q-exact potential, which kills the t-dependence. And therefore, the original quantity of interest, the partition function at t equals 0, can instead be computed by taking t to infinity, which allows you to use. So localization is a case of the saddle point approximation being exact. And it makes the partition function localized to a certain DPS locus, namely the field configurations that are in the cohomology of this potent supercharge. In most cases that look at, it's going to be Coulomb branch configuration. So for the chiral, the n equals to chiral multiplet in a super Yang-Mills theory, can get a VEV. So the partition function is going to be some integral over the n Coulomb branch eigenvalues. And using the fact that this is based on a point, you can sort of the schematic form of the integrand pretty easily. So in a gauge theory, you're going to have a classical action evaluated at the saddle. So this turns out to look like this. But then you also have to do a Gaussian integral from the fluctuations away from the saddle point. So you get a one loop determinant here. So there's some one loop partition function which needs to be worked out. And then you not just one saddle point for each Coulomb eigenvalue, you have one saddle point within each instanton sector. So there's a sum over instanton number which needs to be done, and there's an instanton partition function which accounts for that. So classical one loop instanton, that looks a lot like the beta function for an n equals 2 gauge theory. It's not a coincidence. Seiberg's scheme for renormalizing it polymorphically means that you don't have 2 loops, 3 loops, and so on. You go right from one loop to another. So. But instantons contribute with -1 over g squared, which is like e to the minus n over the tough coupling. So if the tough coupling is fixed, i.e. if you're doing the strong coupling expansion, not the very strong coupling expansion, we can the 1 for now. So we can make things easier by setting this to 1 and then come back to it later. So I guess what I should do is write down the form of this one loop integrand. So yeah, the one loop localization integrand on the sphere. We're mostly interested in getting the partition. Okay, but maybe first it's best possibly like what on earth does this have to do with fixing Wilson coefficients in the graviton or a gluon effort? So the reason why it's related is that localization applies not just to conformal field theories, but also to theories with a mass or something like that. So if you have the partition function or I guess more conveniently, the free energy, which is just the log of partition function minus the log. If you have a mass, if you have gauge coupling, or if you have what's called a squashing parameter. So the admissible backgrounds for this are not just the sphere. You can consider this localization method on the so-called omega background, which is like a squashed sphere. So you can tune the radius and the squashing parameter. If you have the free energy as a function of these various quantities, you can take derivatives with respect to one of these. So you can take n derivatives with respect to whatever parameters you want and then set parameters as 0. And these are associated with deformations away from some more basic action of the CFT. So these derivatives are going to bring down insertions of some operator which multiplies this coupling. And what this will ultimately give you is an integral of an endpoint function of your operator. And that's where this starts to be a connection to, say, 2-to-2 scatter. If you take 4 derivatives of a free energy, that gives you an integral of a certain 4-point function. And it has to be equal, this integral of a 4-point function has to be equal to something that you compute exactly using localization. And therefore you get a constraint other than crossing symmetry on this strong coupling or very strong coupling end. So that's the whole reason for being interested in this concept. So this is very schematic, and we should make it more precise. So one way to make it more precise is to specify z for one loop. So for d n equals 4, first let me define h of z to be the Barnes G function at 1 plus z and 1 minus z. So h of ai minus ij, ai minus aj squared. So n equals 4 super Yang-Mills is n equals 2 super Yang-Mills within the joint hypermultiplet. And you can make this hypermultiplet massive to get what's called the n equals 2 star theory. And then the mass enters in the localization to grant it this way. In the case of 4d n equals 2, you have a single product now. And then here you have a product over the 4 hypermultiplets. Of ai plus the mass, ai minus the mass. And then just to give a sense of what it looks like, I'll write the localization partition function for ABJM2. So oh yeah, that's for the D4 theory indeed. Yeah, hopefully there'll be time for me to say how how you modify it for these cases. But yeah, you can go from one to the other by just sending one of these branes off to infinity. So So separating D3 branes corresponds to moving along the Coulomb branch. Separating D7 branes corresponds to making one of the hypers massive. There are D flows. So I'm not going more about this case, but the nice thing about n=4 and the nice thing about n=2, and they're very different. So here, if you set the mass to 0, this just becomes 1, which means the mass deformation is a deformation around not just any matrix model, but a Gaussian matrix model. So that's quite nice. But it's a double trace deformation because you have a double product here. In n=2, it's exactly the opposite. Setting the mass to 0 does not give 1. So you have, even in the undeformed case, a non-trivial matrix model. But it's a single trace matrix model. And when you add back the mass, it's still a single trace matrix model. So that is nicer than the n=4 case. And this single trace effect, it seems to win out. At the end of the day, the final results we get for this free energy are going to be nicer with n=2 than they are for n=4. So that's a model is nicer from a localization perspective. So that's how you compute the left-hand side of this relation. On the right-hand side, we should be used to the fact that when you take 4 integrals of a 4-point function, you can use conformal killing vectors to really make that just one integral of a 4-point function. And I want to write down what that integral is. So yeah, here. Okay. Take the mu A, the mu D derivatives of the free energy. That's equal to something where you can work it out, and the hardest part is getting the normalization right. So the flavor central charge of a pi is a normalization, and then polar coordinates, and then this u cross ratio to the -2 times the simplest d function of u and v. This scalar box integral is like a polylog, or you can think of it as just the Mellin transform of the constant, or inverse Mellin transform of the constant. Times this auxiliary correlator in the solution to the Ward identity at u and v, where z is our EPI data. N=4 super Yang-Mills has a relation that looks just like this, except there's no flavor symmetry, so there's one mass for this adjoint hyper. I don't know. But this factor is a little bit different. It's this. And some of you might have seen a paper using these in the numerical bootstrap as well. You can do this at small n, and on scaling dimensions along the conformal manifold of n=4 super Yang-Mills. But to do that, you don't just need one constraint, because the complexified gauge coupling has 2 real components. You need a second constraint. So there is a second constraint that you can get in n=4 super Yang-Mills, because with the enhanced supersymmetry, it turns out that the Higgs branch and Coulomb branch operators live in the same superconformal multiplet. There's also something you can do by differentiating with respect to tau. So in general, mass derivatives will give you integrals of Higgs branch operators, of Higgs branch correlators. Tau derivatives will give integrals of Coulomb branch correlators, and squashing parameter derivatives will give you integrals of stress tensor multiplet correlators. So the other constraint is a mixed derivative one like this. Oh, okay. I made a mistake here. That should be c squared. This one should be c. And here there's no d function, just u to the minus 2 h of uv. That is this. And this is the one you want to use simpler. If you have to use both, then you have to use both, but we should expect this to lead to nicer closed form results. In the very strong coupling expansion for n equals 4 superging those, so the result of this including is tons. It has a result which I'll just quote a few terms of. So the central charge is like n squared. We get root n. We should. And then here, there's a non-holomorphic Eisenstein series, E3 halves. And then the next term has another non-holomorphic Eisenstein series, this time of weight 5 halves. And the pattern probably goes on like this forever. At increasingly high powers of 1 over n, you get some non-trivial dependence on the compensified gauge problem. That is what is much nicer in the n equals 2 case. So when we write down the result of this relation, it's going to have non-trivial tau dependence only at the leading order in 1 over n, and then at all the higher over n, but since that series no longer have tau dependence. C is the central charge, n squared. Yeah, so you mean it prepares you, it does a worse job of preparing you for life beyond these first few Wilson coefficients? Yeah, there's an optimist and a pessimist view. Yeah. Yep. Let's say, yeah, this is the result. Yeah. So the modular properties aren't something you have to check for at the end and hope that they hold. Um, we're sort of not smart enough to get the expression I wrote without knowing that they'll be modular invariant, building that into the ensemble. Square root of n. Is that square root of G? N squared goes as yeah. So I don't want to say anything about how this was derived for n equals 4, but I want to say something about how we derive an analogous expression for n equals 2. I hope that doesn't try to lose patience. So given the localization integral with the one loop determinant above, we can expand it at weak coupling. So we Taylor expand the function, that's a known thing. And then we use some correlators with respect to the Gaussian matrix model. This is known, and then the order 1 term is known, the order 1 over n term is known. You can just go as high as you want. For the next direction, you need the connected correlator of these two trace operators. That is something similar. So this at order 1, then plus known stuff at order 1 over n, and so on. So you use a bunch of data like this after expanding the localization integral at weak coupling. You get some series with infinitely many powers of lambda, but it's a simple enough series that what you can do is cook up a Mellon amplitude that recovers that series when you close the contour to the right, and then instead get the strong coupling expansion when you close the contour to the left. So that gives, going to write this. I'm writing it just to highlight some structural features. But by the way, these m's are averages of powers of the 4 masses. That mm, there. And the interesting thing is that this only has 2 types of terms depending on lambda at all. So there's a 1 over lambda term, and then there's a log lambda term. And we knew that we had to get a log lambda term so that log s could become log of s alpha prime when you diverges the string. So this checks out. Of course, I haven't shown what the coefficient of it checks out, but it does. And then the fact that you get 1 over lambda, but you don't get any higher powers of 1 over lambda is this thing that's either good or bad news. You get modular functions at one order, but not at the other one. So it's the constant of the other orders. And now with a view to upgrading this strong coupling expansion result to the very strong coupling expansion, we should consider the following derivatives. So there's, and I'm going to call FB, which is two derivatives by mu1, two derivatives by mu2 of F. And there's going to be Fs and Fc. I'll explain subscripts a little bit. And the idea here is that in the integrated constraint, these four derivatives with respect to different masses labeled by the four cartans of SO8, they relate to integrals of the 4-point function with those adjoint indices. And what you can do is you can decompose this 4-point function with four indices into irreps of SO8 that are exchanged in the tensor product of two adjoints. So you get a bunch of functions of u and v associated with each irrep times the projector onto that. So the index dependence is all soaked up in something like this. And there are 7 representations that appear in the tensor product of two adjoints of SO8. 4 of them I'm not going to mention, but there are 3 related by SO8 triality. So 35-dimensional representation is associated with vector, spinor, and conjugate spinor. And it turns out that these combinations of derivatives, if you look at these projectors and plug them into this relation, this gives you some linear combination of projectors, which is the same as this one, except the V has become S. And this one gives you almost the same linear combination again, except it has become C. So these are naturally associated with the representations of SO8 that are permuted under triality. And then using this expression, you can write down what these things are, and you get various constants and various powers of 1 over lambda. But 1 over lambda, if you want to consider the very strong coupling expansion, you should write this as the imaginary part of tau. And then you should look for modular functions which contain that power of tau and only that power of tau in the perturbative part, and then some non-perturbative completion having to do with instantons, which come with powers of e to the 2 pi I tau. So here we expect Eisenstein non-holomorphic Eisenstein series, which are modular invariant, because SL2Z is a symmetry of n equals 4 super Yang-Mills. So the theory at coupling tau is the same as the theory at coupling -1 over tau. You cannot see that from the Lagrangian, of course, but you can see that from the Seiberg-Witten curve. For these n-2 gauge theories, the situation is a little bit more involved. So the theory at coupling tau is only equivalent to the theory at coupling -1 over tau if you also act with an SO8 triality transformation. So we shouldn't expect Eisenstein series here. We should expect modular functions that are permuted among these 3 under SO2Z. And we could think of one solution system with everything, and that was of V this. Plus some function of n, but not tau. And then for fs, it was theta 2, theta 4. And for fc, it was theta 2, theta 3. So in the weak coupling expansion that we did to get this, we neglected, so we had some Mellon amplitude where we closed the contour way to get to, we closed the contour of the other coupling expansion. But we could have also considered the arcs themselves. And there's a paper by Beccaria, Dean, and Cyclone which does this. So they consider all the masses to be equal, so they don't quite have this expression, but they have a very expression, and then they also add some contributions of the arcs. So they keep e to the minus root lambda coefficients, but they drop instantons because they start from the localization matrix model with z instant equal to 1. They drop these e to the minus n terms. And what we've done here, by finding a modular upgrade of the weak coupling expansion, well, of strong coupling expansion, we have dropped the arcs, which are now e to the minus root n, but we have kept the instantons. And the next thing to do after guessing this is to try to see if we can recover it from an honest calculation using the instanton partition function, which has been computed by Nekrasov and Shadkin. And we were able to verify this up to 2 instanton order. And I would love to be able to tell you that we stopped at 2 instanton order because we were lazy. But in fact, we stopped there because there are problems going to a higher number of instantons. And these problems are somewhat familiar in other contexts, especially 5-dimensional gauge theories. So the instanton partition function is a sum of k instanton partition functions times q to the k, where this is some integral over the instanton moduli space of these indices of the so-called ADHM quantum mechanics. So there's something associated with the gauge group, something associated with fundamental hypers, something associated with the anti-symmetric hypers, and so on. And there are a lot of papers about the fact that the instanton expression, the instanton partition function is given by this expression, except when it's not. So there are some extra degrees of freedom that are somehow missed by the ADHM construction, which means what you should really consider is and taking the expression for Z extra that's known in 5 dimensions and compactifying it to 4D turned out to be very hard. We didn't know how to do it. So we ended up guessing this by other means. So there's this whole story of wanting the instanton partition function for one gauge group to equal the partition function for another gauge group if the groups are isomorphic. So SU2 and USP2 is an example relevant for us. But getting that to work is not always because you have to worry about schemes and redefining what you mean by Q. So by going to rank 1, so SU2 and USP2, by demanding that these were isomorphic, at 0, 1, and 2 instanton order, we could solve for Z extra in that low rank case and find that it was independent of the Coulomb branch eigenvalues and therefore easy to generalize back to the high rank case. But at 3 instantons, it was dependent on the Coulomb branch eigenvalue, and therefore we didn't know how to generalize it. So that's why we could get this result by guessing, and we could get this result up to 2 instanton orders honestly, but we could not do it at higher instanton orders. So I think that's a very important thing to work on. Yeah, so using like rigorous. Well, yeah, I mean, I'm definitely okay with assuming it, but the yeah. So the space of modular forms is what you're talking about, right? Yeah, I think this result is very solid. So I guess the motivation for studying instanton would be if you're genuinely interested in the instanton modular space. So I'm wanting to talk about the non-Lagrangian n equals 2 theories a little bit. 5-10 minutes. Okay. Yeah, so the non-Lagrangian n equals 2 theories are sort of a bit in their infancy right now. So we couldn't fix as many Wilson coefficients as we could for this gauge theory with SO8 flavor symmetry. Um, so I mentioned that there's a log lambda over n squared in the strong coupling correlator. And in the very strong coupling expansion, this becomes, of course, log of n over n squared. And this is what we were able to fix from localization in the Argyres, Douglas, and Minahan Nevichansky cases. So we have much hope of being able to approach these by expanding the partition function, because um, even if those partition functions don't have this issue with z extra, they do require us to plug in tau equals I or tau equals e to the pi I over 3, which is a large number. So we're going to need to resum the whole thing, keep track of infinitely many terms. And these terms, as evaluated by Nekrasov and Shad, can become very complicated. So we don't know how to resum them. So instead, we use the formulation of the localization matrix integral. Instead of writing these Barnes G functions, we write that it's an integral of the exponential of the Seiberg-Witten free potential. And these epsilon1 and epsilon2 associated with the omega background, we're taking epsilon1 equal to epsilon2, so there's no squashing. But the radius of the sphere, okay, but the product of them is 1 over the radius squared. So we can write this as, in this special case, as e to the minus radius squared times the Seiberg-Witten free potential. So if we knew this object on a sphere of radius r, then we'd be done. We'd be able to do this integral and get an expression just like that one. But the original papers of Seiberg-Witten are concerned with computing this in flat space. And computing this on more general manifolds can be very difficult. So what we ended up using was an expansion where how to write this? What radius r, the potential is the flat space one plus the log of some discriminant, which was written down by Shapiro and Tachikawa. Times the product of some rank one discriminant plus some additional terms. And then we notice that this log is the only one that can contribute to log f. So we need to use two terms in the prepotential. And the way you get the prepotential is if you've seen these period integrals in Seiberg-Witten theory. So with respect to this gauge invariant coordinate on the Coulomb branch, which is the Coulomb branch eigenvalue plus quantum corrections, these eigenvalues and their dual with respect to the coordinate, they're going to period integrals around the different period Seiberg-Witten curve, where the Seiberg-Witten elliptic curve can conventionally be written in this form. So G2 and G3 depend on U and they depend on the mass. And you can look up what G2 and G3 are for Argyros-Douglas and Minahan-Nemechensky theories. This has been very well studied by the scaling limit of the Seiberg-Witten curve for gauge theory. And okay, so calling this derivative the first period, there's a very nice result relating the Eisenstein series to the first period and these. So by working with this integral and using some hypergeometric identities and transformations, G2 is this holomorphic Eisenstein series at tau, which is either I or e to the pi I over 3, over some power of the first period. And then G3 is going to be the same thing, but with E6 and omega 1 to the 6. So you can use these and the known values of G2 and G3 in Argyros-Douglas and Minahan-Nemechensky theories to get the prepotential, because the coupling is just of these. And then you can solve for the mass deformed prepotential. So this, you can just use the fact that this is related to coupling. This is like the Lagrangian of in the superspace, for example. So because this, because these n equals 2 Lagrange field theories are very nice, the rank n potential is just a sum of rank 1 prepotentials. So if you can solve for the rank 1 prepotential with a mass deformation, then you're done, because then you'll have this expression, and you also have the rank one discriminant of the Seiberg-Witten curve and the this part that's no longer a single trace found by Shapiro and Tachikawa, and you can find it, and what you ultimately get is the coefficient of the log here, which allows you to play the same game as before, take four mass derivatives, and predict this log n part of correlate. So I don't have time to say much more. And maybe one last thing I'll say is that for to really get this at the same level as the Lagrangian n equals 2 theory that we could do, you need to know not just log n, but you need to know the other protected vertices f to the fourth and b squared f to the fourth. And those genuinely depend on infinitely many corrections to this potential around flat space. And the way that you would compute these is from an anomaly equation, which has history to topological string theory, but it's either called the holomorphic or modular anomaly equation because it's all about characterizing how this potential depends on E2, which is an Eisenstein series where you can choose holomorphy or modularity, but not both. So if this F is a sum of say like genus G terms, then the derivative of Fg depends on the lower genus. But it's nonlinear, so it's kind of tricky. And there's been some recent work in using this systematically in various cases. But this is how you would proceed to try to get more information about the foregluon amplitude to non-Lagrangian and equals to SCFP. I think I've gone over time, but thank you for listening. Hope it was interesting. So we've reproduced things we've known before from a different perspective, which can be enlightening. So the maybe an early example of this was in ABJM theory. There was this so-called absence of E4 R to the fourth, and this was shown from localization, and it was previously thought to be the case because of consistency with string dualities. So this fact about the flat space effective action was reproduced. In the 3n equals 4 case done recently, there was it's the absence of trace f to the fourth, and I don't know if this was previously known. Are you familiar with this? Yeah, so that's a basic structural fact that that could be. I haven't seen evidence that it was known before. And then, and when we say that we check this log n against the flat space limit, I think these flat space calculations are still a little bit new. There wasn't a paper which clearly said that the log n threshold term in flat space should be this. It was sort of, I mean, the flat space calculation was certainly easier than the ADS one, but if it was known, it probably wasn't well known. No. Yeah. So good. I was trying to see how high the expansion has been pushed, and I could only find these six, be the sixth or the fourth. So I'm optimistic about combining this with Aldine Hansen's method of using single value dispersive samples. Yeah, I think that's going to be ready. Combining these is probably less of a long shot than using the pure spinner string theory in ADS right now.